The aim of the talk is to basically give a complete proof of this. But before I start with the proof, just a bit of quick background to motivate the question. So let me start with the questions on ZD, where they were originally studied. So we just have P in 0, 1. And for each edge, we declare it to be open independently with probability P. And I write P sub P for Bernoulli percolation. Okay. And it's easy to see that there exists some parameter in the interval 0, 1, below which there exists no infinite cluster almost surely, and above which there exists an infinite cluster almost surely. And the region below PC is called the subcritical region, and the region above PC is called the supercritical region. And the basic question you can ask, so starting with the subcritical region, is how big are the clusters? And it turns out that they're as small as they can be. So sharpness. So in the subcritical regime, basically the probability that the connected component of the origin is bigger than some n decays exponentially in n. And this is the best you can hope for. And so this was proved in 1986 by Menshikov and simultaneously, roughly, by Eisenman and Barsky. And since then, there have been many simpler proofs. So for instance, Duminil-Copin and Tassio, then another proof by Duminil-Copin, Raufi and Tassio, and then more recently a proof by Vanderbilt. So somehow this side of PC is well understood, at least the question of sharpness. On the other side, what you would like to say is that the finite clusters are as small as they can be. So what's true is that the probability that the connected component of the origin is large but finite, decays exponentially, and this time not in n, but in phi of n, where phi of n is the isoperimetric function of the graph. So phi of n is the smallest boundary you can get for a set of size n. So it's the infimum of, let's say, the edge boundary of S over all subsets, finite subsets of vertices of size bigger than n. Okay. And this was proved by Grimmett and Mastra. In 1990. Okay, so this is the story of sharpness for ZD. And then after 1990, in 1996, Benjamini and Schramm initiated the study of percolation on general transitive graphs. So one of the motivations behind this was to understand which results of percolation on ZD depend on the specific structure of ZD and which just depend on basic symmetry. And so let me just recall what a transitive graph is. So we write G equals VE for an infinite transitive graph, and we always assume that it's also connected and locally finite. So just some basic examples. So of course, ZD. You can take also a kind of different looking graph, a regular tree, infinite regular tree. or more generally, a Cayley graph of any group. So these are just some examples. And you can ask the same questions for Bernoulli. Yes? Yeah, these are the vertices of ZD. Yeah. So if you view ZD as a graph, this is, yeah. And you can ask the same questions for Bernoulli percolation on ZD, but yeah, so let me say what's known in this general setting. So subcritical sharpness. So it turns out that the proofs of subcritical sharpness carry over quite easily to this general setting. However, supercritical sharpness didn't follow from the argument of Grimmett and Marstrand. So roughly speaking, the proof of Grimmett and Marstrand works as follows. You start with P slightly above PC, and then you zoom out, and the percolation looks like another percolation on ZD with P very close to 1. And then for P very close to 1, sharpness, supercritical sharpness is easy. And so here you crucially use the self-similarity of ZD, which is unavailable for general transitive graphs. So therefore, supercritical sharpness remained open in general. So there have been certain special cases where supercritical sharpness was shown. So most notably, in 2021, Herman and Hutchcroft showed supercritical sharpness for non-amenable graphs. So non-amenable just means phi of n. Oh, yeah. So the boundary of a set is proportional to the size of the set. And in 2024, Contreras, Martineau, and Tassion showed it for graphs of polynomial growth. So those graphs that resemble ZD. But supercritical sharpness remained open in general. And I would like to now present a kind of elementary proof of supercritical sharpness. So to begin with, let me begin with a basic lemma, which is the starting point of our proof. So the title of this section is called Touches Are Costly. Okay, so in this section, let me work on a general graph, need not be infinite or transitive. The G. And in anticipation for what is to come, let me fix two vertices, one of which I'll call infinity. And I consider the standard monotone coupling of Bernoulli percolation on this graph. So these are Bernoulli percolation for every parameter P between 0, 1, coupled in the standard increasing way. And this, the first lemma says that it's exponentially unlikely to have two clusters at different parameters that don't merge but come close to each other, right? So let me, so consider, so let, which one did I want more? So consider two parameters between 0 and 1 and consider the following event. So you look at the P cluster of the origin and look at the Q cluster of infinity. So these are just fixed vertices. And look at the event that they do not merge, but they share T edges in their boundary. Okay? And the first lemma says this is exponentially unlikely in T. So the probability of this and this is, it's convenient to write it like this. Okay, so is the statement of the lemma clear? You have the P cluster of the origin and the Q cluster of infinity, and we're looking at the event that these clusters are not the same, they're disjoint, but they come close to each other in T places. Okay, proof. Let me do a proof by picture. So first, just explore the cluster of infinity in Q percolation. So if this event is to occur, certainly this cluster cannot eat up zero. And in revealing this cluster, we have revealed some Q closed edges on the boundary of this cluster. Next, explore the P cluster of the origin. If we are to have at least T touches, so explore the P cluster of the origin in the complement of what we have explored. So we have explored all edges incident to this cluster in Q percolation, and in the complement, so in the graph induced by the complement of this cluster, explore P percolation, the P cluster of the origin. And if this event is to occur, this cluster must reach the Q cluster in T places. Now we know these clusters are Q closed, but we do not yet know that they're P closed. And in order for these clusters to remain disjoint, we further require these clusters to be P closed. So for each of these edges, we pay the probability of the edge being P closed given that it's Q closed. And that's just this. Okay, so that's basically the proof. So that was the first lemma, just a basic one. And the next section is to reduce the supercritical sharpness statement to a statement about touches. So actually, I didn't state the theorem. Let me just write it here. And so the theorem in the end, which we want to prove, is that, so we go back to the setting of infinite transitive graphs. So here, this applied to any graph. So let G be infinite transitive. Then, for all P bigger than PC of G, the probability under P that C0 is bigger than N, but is finite, decays exponentially in phi of N. And if you are interested in radius of the clusters, the same proof basically also gives that the probability that zero is connected to distance N, but not to infinity. This decays exponentially in N. So I won't talk about this, but basically the same proof works. Okay. So the goal of this next section is, so it's called many touches suffice. Is to reduce this theorem to a statement about touches, and we'll use this lemma. So, okay, so G is a transitive graph, and the second lemma. Okay, so first, let me state this lemma in a way that, so in the form that we cannot actually prove, but is more natural, and then I'll modify it into the lemma which we actually can prove. So let Q be bigger than PC. There exists delta, so let me leave some space. So there exists such that for all sets, let's say containing the origin of size bigger than equal to N and connected. So think of S as a possible realization of the cluster of the origin. The following event has constant probability. So what's the event? So I have this set S, which contains the origin and has size at least N. and I look at the event that the cluster of infinity in the complement of S in Q percolation touches this set S in order phi of n places. So I look at the event that the cluster of infinity, the infinite cluster, just again, because this is the key event, we look at the event that this fixed set S, which has size bigger than or equal to n, is touched by the cluster of infinity in at least delta phi of n places. This event has probability at least delta. Now, let me show that lemma 1, lemma 2 as stated, plus lemma 1 implies the theorem. And then let me modify lemma 2 into the lemma we can actually prove. And it will be clear from this proof that that's also sufficient. Okay, so we want to prove the theorem. So let P be bigger than, so we are given P bigger than PC. Choose an intermediate supercritical parameter Q and consider the following event. Consider the event that the cluster of origin in P percolation has size at least n, and that the cluster of infinity, which now I treat as a point, touches the cluster of the origin in delta phi of n places. So I look at this event. The event that the cluster of origin in P percolation is large, and on the outside, Q percolation allows you to come from infinity to this cluster in many places. Now, by lemma 1, this is exponentially unlikely in delta phi of n. Okay, so there's this subtlety of treating infinity as a point, but that's really not an issue. What we actually do is work in a large ball and treat infinity as the boundary of the ball. But taking that for granted, lemma 1 immediately gives that this is smaller than P minus Q delta phi of n. Now, let's lower bound this event. So one way to achieve this event is to first grow the cluster so that its size n and finite, and on the complement use lemma 2 to create many terms. So we can say that this is at least probability in P percolation that the cluster of the origin is at least size n but finite. And in doing so, we have just revealed the edges incident to this cluster and nothing on the outside. And then we apply lemma 2 on the outside to create many touches. So by lemma 2, with probability delta, we can achieve this event. And just rearranging, we immediately get that the probability that the cluster of the origin in P percolation, the probability that it's large but finite is exponentially small in pi of n. Okay, so it's clear that this version of lemma 2 implies, and lemma 1 implies the theorem. But now notice that it's not necessary that we have delta here. We have an exponentially small number in delta phi of n here. If we also had an exponential in delta phi of n, just so that it doesn't compete with this P minus Q delta phi of n, that would be sufficient as well. So let me modify the lemma into the lemma that we can actually prove. So lemma 2 is for all epsilon greater than 0, there exists delta such that this probability Okay, and why is this enough? So if we have this lemma, this, you will get delta phi n. And so what epsilon should we choose? So let epsilon be, let's say, p minus q over 2. Then we will get probability that the cluster of the origin is large but finite, is smaller than e to the power minus p minus q delta phi n. And then taking this to the other side, you get e to the power epsilon delta phi n. And since p minus q is larger than epsilon, you still get an exponential bound in phi. Okay. Is this clear? Yeah. Yeah, here it's all in Q percolation. Yeah. So when we apply this lemma, we just apply it to the outside in Q percolation in order to create touches from infinity with exponentially good probability, but the base of the exponent is arbitrarily close to 1. And it's important that this epsilon doesn't depend on the set.
Can you describe the event in lemma 2 again, please?
Sorry, can you repeat?
Can you describe the event in lemma 2, please?
Yeah, this event. Yeah. So this event, so you have a fixed set S of size at least n, and the event is in Q percolation outside the set. So in the graph induced by the complement of S, the cluster of infinity touches S, if you count the number of edges in the boundary of S, in at least delta phi n places. Okay, so now the rest of the talk will be devoted to proving lemma 2. So the strategy is to create one touch at a time, and in the end, we want to create delta phi n touches with good probability. So before I describe the final strategy, let me describe a toy version of the strategy. So we want to prove lemma 2. So we are given some q bigger than pc. And for the sake of analysis, we would like to split this q into a supercritical parameter and a sprinkling. So let p and eta be such that pc is smaller than p plus eta, smaller than q. Okay, so this ensures that the union of p percolation and an independent copy of eta percolation is dominated by q percolation. So I'll work with a union of p percolation and eta percolation and prove the lemma for this, and then it will imply it for q percolation. Okay, so here's the toy strategy. So we're given some set S. Maybe I draw it like this. So the first step, what we would like to do is to choose a point and explore its P cluster in order to create one touch with constant probability. So in this toy strategy, I won't try to get 1 minus epsilon to the delta phi n. I'll just try to get constant to the power delta phi n. And then I will tell you how to improve this to 1 minus epsilon. So the first step is to choose a point to explore and create one touch. Okay. So what we know is that in P percolation, in the entire graph, since it's supercritical, it has constant chance to go to infinity. Okay? Therefore, in the graph, in the complement of S, every point has constant chance to either go to S or to go to infinity. So a point close to S might typically go to infinity through S, maybe here. And therefore, we can only say for every point, it basically has constant chance to go to S, so the boundary of S in the complement of S, or constant chance to go to infinity. Now we would like to choose a point which has decent chance to both go to S and both go to infinity. and we slide this point starting from S towards infinity. So right at the boundary of S, it satisfies the first option. With probability 1, it goes to the boundary of S. And as we slide this point to infinity, it satisfies the second option. And therefore, there is a point somewhere in the middle which satisfies both options, perhaps with a different constant.
So when you say this constant chance of going to infinity, you want like without hitting S.
Yeah, without hitting S. So in P percolation, in the complement of S, it has constant chance to hit boundary of S or constant chance to go to infinity. And this is just because P is supercritical. And then by basically an intermediate value argument, sliding this point from S to infinity, we can find a well-positioned point which has, maybe for a different constant, has good chance to go to the boundary of S and good chance to go to infinity. And now we simply explore its P cluster. And with constant chance, we get a picture like this. This is P cluster. And okay, so let me make a tally. So number of touches and the probability. So in the first step, we've got one touch with probability maybe by FKG, C squared. Next, we repeat the argument. So let me call this C1. We choose a point that is midway between S and C1 union infinity. Okay? So we would like to create another touch. So we would like to grow this cluster C1, maybe using the sprinkling to glue stuff, to create another touch. So now we choose another point which is midway between S and C1. Okay, so let's say we choose this point and explore its P cluster. And maybe this one doesn't go to infinity, but tries to glue to C1. Of course, we have already revealed P closed edges here, but we can simply use the eta percolation to open an edge and get another touch with probability C squared eta. Okay, and notice that we can continue like this as long as we have not exhausted literally all exposed boundary edges of S. Because if we have a boundary edge of S, we can take a path to infinity and then slide our point until it either hits the previous cluster or goes to infinity, and starting from S, and find an intermediate point which is midway between the previously explored clusters union infinity and S. So we can continue like this. Yeah.
How do you, can you just repeat for the second cluster? It's an exploration of what? It's another point which satisfies?
Yes. So this, the second point, has constant chance in the complement of what's been explored to connect to the boundary of S, or to go to infinity union the previously explored cluster. And when I say go to, I mean go to the boundary of, and then we sprinkle to attach it. Okay, and we can continue like this as long as we haven't exhausted the exposed boundary of S. So in fact, this argument will give that the probability under Q percolation, so actually P plus eta percolation, which is dominated by Q percolation, that the number of touches, in the sense of that picture in lemma 2, the probability that it's bigger than the exposed boundary of S, so all edges in the boundary of S that go to infinity outside S, so I call that del infinity S, is at least C squared eta del infinity. But now notice that this cannot be good enough to prove lemma 2. Firstly, because phi hasn't played a role at all. And for example, for this set, the exposed boundary, which includes everything, is much bigger than the phi of n. Right? So the phi of n is probably the boundary of this kind of smoothened version of this set. And so we've gotten way too many touches. And the second reason why this cannot be deep is that if you imagine this question on ZD, so if you imagine some connected set on ZD, we know that the boundary itself is connected. So one way to achieve this aim is to literally connect up the boundary and then send one point to infinity. So we can achieve this in a kind of trivial way on ZD by just paying for the entire boundary of this S, which is like a surface, to be connected and send it to infinity. So all this midpoint stuff wasn't necessary. So clearly this can't be enough to give lemma 2. But now I'll describe the improved version of the strategy, which is really the heart of the proof, which allows you to do that. Okay, so the key idea here, the first key idea, is to replace points by large balls so that they connect with high probability instead of just constant probability. Okay, so improved strategy. So we're given Q bigger than PC, and here let me split this Q into one supercritical part and two sprinklings. So let P and eta be such that PC smaller than P plus 2 eta smaller than Q. So we want to create touches at Q. Instead, we will create touches in the union of one copy of P percolation and two independent copies of eta percolation. And this union is dominated by Q percolation. Okay, so the first idea, so let me draw the picture here. So we have also been given a fixed set and also some epsilon bigger than 0. Okay, so in the end, the goal is to show that we can create delta phi and touches to S from infinity with probability 1 minus epsilon delta. Okay, so the first idea is, instead of points, to aim to explore large balls. So large in the sense that there'll be a fixed radius independent of S, but they go to infinity now, not just with constant probability, but with probability close to 1. So choose R big such that the probability in P percolation, which is a supercritical percolation, connects to infinity with probability 1 minus some suitably small function of epsilon and eta. Okay, I won't specify it, but it will be clear what it requires, what it needs to satisfy. Okay, so we choose a large ball, and it's easy to choose an R such that it connects to infinity with high probability. And now the aim is to explore that ball. Okay, so now what's the analog of this thing? It's what's called the square root trick. So every ball in P percolation on the entire graph goes to infinity with high probability. And therefore, in the graph without S, it goes either with high probability to the boundary of S or with high probability to infinity by the square root trick. Okay, square root trick or the FKG inequality. And again, we do the sliding business. So we start with a ball close to S. If it literally intersects S, it goes to del S with probability 1. And then as we slide the ball to infinity, it starts preferring infinity. And therefore, we can find a mid ball which goes to S and to infinity with high probability, where this high probability is governed by maybe 1 minus square root of epsilon. And then we do the same thing. What we aim to do is to explore the cluster of this ball in order to create a touch, now with high probability. And we want to repeat this. Okay, but now there's the first problem. This cluster is not really a cluster of infinity. There's no reason for this ball to allow a connection between the part that goes to S and the part that goes to infinity. Okay, so how do you solve that? One way perhaps you can solve that, or try to solve that, is to just ask for this ball to be open completely in P percolation. But of course, then you can't do things with high probability, right? Paying for the ball to be open in P percolation completely is very costly. Well, then you can say, maybe I look at many balls. It's still a bounded number in terms of R and epsilon and so on. And look for a ball that connects, that is entirely open. So somewhere in my graph, maybe I start with this intermediate ball. It wasn't entirely open, just a bit was open. This was open. And then it turned out that this was completely open. And then I can say I explore that. But there's a problem that these negatively revealed information in P-percolation might interfere with your exploration of this ball in P-percolation. So the fix to that, and that's the first key idea, is to just use an independent layer to reveal the balls. So you look for an open ball in an independent low density percolation of parameter eta. Let me draw that maybe in red. So I can erase it and do the procedure again. Okay, so you look for a ball and check. So look for a ball which is midway between S and infinity, in the sense that it connects with high probability to S and with high probability to infinity, and check if it's entirely eta open. Maybe it's not. But eventually, in a certain L steps, so let me write, so choose L big enough, huge. So in terms of R, epsilon, eta, and so on, such that, I won't write it, basically, if I look at L disjoint balls, one of them will be entirely open in eta percolation with probability, with high probability, say 1 minus epsilon over 3 or something. Okay, so we find an entire, sorry, I should draw that in red. We find an entirely open ball in eta percolation. So, and then we exploit P cluster to create a touch with high probability. And now it's really a cluster of, it's part of the cluster of infinity. Okay, so let me do a similar tally. So this one was not necessary. So the number of touches and the probability. So we've achieved one touch with probability. So with 1 minus epsilon over 3, we found an open ball within the first L tries. And let's say the F was chosen so that this high probability is 1 minus epsilon over 3 as well. So with 1 minus epsilon over 3, additionally, we created a new touch. Now, what's the second step? The second step works the same as in the toy version. We find a ball that's midway between the previously explored cluster C1 union infinity and S, and exploits P cluster. And with high probability, it either just goes to infinity or comes and touches S. But again, we have the problem that it's not really connected to C1. But since it connects with high probability to C1, provided that F was chosen sufficiently large, if we allow ourselves eta percolation on the boundary to glue, it will glue with high probability. So this F needs to be chosen suitably larger so that even after exploring the P percolation, and instead of doing P percolation on the boundary of C1 or the common boundary of C2 and C1, which we're not allowed to do because we've already explored P percolation, but just doing eta percolation, the probability that it glues is very high. Okay, so in this case, I forgot to say, so here as well, we look at intermediate balls first. Maybe they are not open, and wait for one within the first L steps that's entirely eta open in the first copy, let's say, and then we use this gluing in the second copy, and all the big exploration is in the P percolation. Okay, so in the second step, we created a touch with probability 1 minus epsilon over 3 to find an entirely eta open ball in one of the copies. 1 minus epsilon over 3 for the C2 to glue to S and the previously explored place, and 1 minus epsilon over 3 for the sprinkling to glue. Okay, and we can continue like this. So let me do maybe one other step. So maybe, and maybe this one just goes to infinity on its own, and so on. Now the question is, when can we get stuck? And that's exactly where phi will come in. And so note that these p percolations can go over this pink one because it's an independent peacock. Okay, so now the question is, and that's really now the key final step, is to understand when this procedure gets stuck. So note that if we have a kind of thickened path which leads, so suppose we're at this step, and suppose we have a kind of thickened path. So what do I mean by thickened? Big enough to admit R balls from the boundary of S to infinity or the previously explored region. We can do this intermediate value argument by sliding this ball along this thickened path to find an intermediate ball that connects to both. But when can we not do that? When literally this red stuff always lies on every thickened path and kind of blocks us. And so we have to look for balls in a previous red region, which we're not allowed to do because we're looking for balls in red. Okay, and that literally happens when kind of this red forms a cut set around yourself. So let me draw the bad picture. Yeah, so I want to say that I can run this procedure for 5n steps. So to get stuck, we basically must have the following picture. Let me draw kind of a different, let's say S was like this, bigger than equal to n. Let's say the cluster of infinity really was coming to try to touch. So maybe it looks like so the cluster of infinity is just the outside. So the shaded part is the cluster of infinity. And of course, we have red balls everywhere. Maybe some successful ones, which we used before, some failed ones. All disjoint, of course. I don't draw it exactly disjoint. And so on. So they're just spread out across space. Now, in this situation, it's not necessarily possible that we can find an intermediate ball to explore. Because you see, so these are all the previously created touches. If we do the sliding argument, what we need to do is start with an edge and take a thickened path to infinity or the previously explored region, and along that find a suitable ball. But maybe they always lie on this pink region. So now we're stuck. But now imagine I'm at step K, where K is some very small constant times phi of n. So maybe some smaller than some delta phi of n, where delta is really small. And suppose we have not created delta phi of n touches already. If we have, we're done. In these steps, in each step, we create at most order L amount of red stuff. And so therefore, the total amount of red stuff is still order phi of n. And therefore, if this is not order phi of n, this red stuff cannot form a cut set, right? Because we have not done enough steps to create enough red stuff. So this scenario can never occur in a step which is much smaller than delta phi of n, which means I can always do the procedure for one more step. And therefore, I can run this procedure guaranteeing successes for delta phi of n steps, unless I already created delta phi of n touches before. Because the previous touches, along with the red stuff here, the only bad scenario is that it forms a cut set from your set to infinity. Okay, and that's the end of the proof. You create delta phi of n touches with 1 minus epsilon to the delta. Okay, and that's, thank you.
Yeah, other questions? Okay, so let's thank Ritvik again for a very nice talk.